In this video, we'll look at the difference between delta G and delta G standard. And delta G standard, so when we write that little degree symbol there, or what looks like a degree symbol, that tells us that we're under standard conditions and our reactants and products are in their standard states. And normally all we have to worry about is that gases are at 1 atmosphere, solutes are 1 mole per liter, and solids and liquids are pure. So when we do a chemical reaction, so for instance, let's go ahead and write the reaction for water evaporating. So we take water in the liquid phase and we turn water into the gaseous phase. We can calculate delta G standard for that reaction at 25 degrees C. And we can do it a number of ways, right? We can look up the heats of formation of products and reactants, the molar entropy of products and reactants, and we can combine to form delta G at 25 degrees C. Or we can just use the heat of formation, the Gibbs energy of formation of this and subtract it away from this. Whichever one is the easiest to use, you're welcome to do it. This gives us positive 8.59 kilojoules per mole. So we look at that and we say, oh, that means it's non-spontaneous, right? So the traffic light is red. So the question is, does water evaporate? And we are all familiar with the idea that if we take a glass of water and we leave it over time, the water will evaporate. It doesn't boil, but if we come back in a day or two, we will find ourselves with an empty beaker. So how do we rationalize the fact that thermodynamics says it can't happen, but our everyday experience says that water does evaporate at room temperature? The solution to this dilemma is to realize that what we've done is we've calculated the reaction under standard conditions. So what exactly do I mean here? Well, we start with pure water, which is totally fine, and we convert pure water to 1 atmosphere of water vapor. And it turns out that we will never be able to convert water to 1 atmosphere of water vapor because that is the boiling process. Now we know that water does evaporate, but it only gives us a vapor pressure of somewhere on the order of 23.8 millimeters of mercury. So it doesn't get all the way up to 1 atmosphere. In fact, it doesn't get all the way up to 1 atmosphere until it starts to boil at 100 degrees C. So that makes sense. So our reaction can actually occur as written, but it can't actually produce a standard state of water vapor. It can only produce water at a fraction of 1 atmosphere. So of course, this throws down the gauntlet, right? So how do we calculate delta G under non-standard conditions? So how do we calculate, whether water will evaporate and give a vapor pressure of 10 millimeters of mercury or 20 millimeters of mercury? How do we know if that is allowed? And so that means that we have to calculate delta G instead of delta G standard. And there's a very nice equation for this that we're not going to go ahead and derive. We're simply going to write down. However, in physical chemistry, we will derive it, and we will see that delta G under the actual conditions is delta G under the standard conditions plus a correction factor that is R, the gas constant, T, the absolute temperature, and then the natural logarithm of Q. And remember, Q is our reaction quotient. So this is our reaction quotient. So essentially products over reactants. T is our thermodynamic temperature in Kelvin, and R is the gas constant. And because we're working with units of joules for our energies and our free energies, this is going to be the one that is 8.3145 joules per mole Kelvin. So I apologize, we keep using 2 different values of G. If we're dealing with primarily atmospheres and gases, we'll use the 0.082061. If we're dealing with energy, we'll almost always be using the 8.31451. So there you go.